First of all, I would like to thank Techno College of Engineering Management and especially Professor J.R. Kayal, for inviting me to this workshop. So I attended this workshop last year also, which was held in NIT Agartala. There I spoke about the seismic hazard analysis and the seismic zone maps. So today's lecture also will be something like continuation of what I spoke last year also. So today I speak about the seismic response of Indo-Gangetic Basin. Now this problem is a one of the most difficult and challenging problem in Indian seismology, and then you see this earthquake engineering. Of course, yesterday we had very nice lectures by the both Russian professors, So Professor Rubin and Professor Antonia, they have already introduced you to the subject of soil amplification, then hazard analysis and everything. So my lecture will be, is a continuation of whatever they spoke, yesterday itself. So anyway, so to start with, I'm just showing you this seismic zone map of India, which is in IS 1893. Most of you, would have seen this zone map. So you would have seen this things, you would have seen this in your IS 1893. So you would have seen this in your, this IS 1893 in your codes. You would have seen this one. So the whole India is divided it into 4 zones. Okay. And then Agartala, if you see, it lies in zone 5, which has a PG of 0.36G. Most of you, would have seen this one. Now, the main problem with this map is almost 25 to 30 years old, the map is. And then this map is also based on some past damage, the earthquake intensities. And of course, a little bit of geology is also involved in developing this map. So now, there has been effort to update this map, to develop a new seismic zone map, by this probabilistic seismic hazard and of course deterministic analysis, and to develop a new hazard map based on hazard analysis. So this project was awarded to us 3-4 years back by NDMA and of course monitored by Bureau of Indian Standards. So we have made some progress with this, the seismic zone map. So this I'm showing you the new seismic zone map, which was a tentative kind of thing. We had a meeting even yesterday afternoon also to discuss about this one. So overall things have been agreed, but some small, things are taking place, like some small adjustments and here and there. And now the methodologies, how we arrived at the seismic hazard map, I spoke in the last year's lecture also, and that lecture is available in YouTube. I will show you that link also. So if you are interested, you can go to that and you can find out, what was the methods, how did we end up with these type of maps also. So now the main problem is, so now this zone map, whatever we have developed, say, so this is, based on, of course, PSHA, DSHA, maximum of these two, but it is valid for rock site actually, some 760 meter per second itself. So this zone map, are the values, say, you can directly use in peninsular India or at places where you see the rocks. But when you're having a sediments, say, okay, so now, how do we handle this one, and how do we, bring this map to the surface level by incorporating the soil amplification, other things is a main challenge, and that is where, things are stuck. So now if you see this geological map of India, so most of you would have seen in your engineering geology course or soil mechanics course in your second year or third year. So this is like a broad map produced by geologists. They say that the whole of this yellow colors, whatever you see here. So this entire thing is of alluvium itself actually. Okay, the soil deposits are there. So now how do we estimate you see this hazard for the sediments also. Now apart from Indo-Ganga Basin, there are also small basins are there near the river mouths, Godavari River, Krishna River here also, like small the sediments are there. So now how do we estimate you see the hazard analysis for our whatever values we have got, say. So now how do we estimate this, bring the hazard to this sites also. So this is the main the challenge. Now another thing also, if you say like yesterday Russian professor's lecture, they have shown you the amplification. Okay, that is a one-dimensional amplification. They have shown you why soil amplifies because of impedance, contrast, and other things also. And they have also shown you that shake, equivalent linear, that analysis also they have shown. Now, recently, in the last 20 years or something, people have been talking about this basin effects, basically. So basin effect essentially means, the shape of the basin, say, that also, plays a major role in, so that also plays a major role, in this amplification also. So like for example, here I'm showing you, this is a typical basin, like we say foreland basin we say. Now you can have a parabolic basin also, or the basin shape basically, how the sediments are same soil only, but if it is located in this type of shape say, or this type of a shape, or if it is a rectangular basin, or if it is a trapezoidal basin. So now the results are entirely different. Apart from soil, the shape of the basin also plays a major role. I'm just showing you some graphs like amplification say for velocity. If you see, so this is in a typical parabolic basin. Now if you see trapezoidal say, entirely different. Even the frequency content also, they're very entire different itself. So which means this basin plays a major role apart from the one-dimensional soil amplification. So this is a major observation which has been done in the last 10 to 20 years. Say the basin also plays a major role in this amplification. And now if you see the existing our IS 1893 is how it handles amplification, So right, you could have seen the code, they define type 1, type 2, type 3 based on SPT, that standard penetration test. You have to do that N value, and then you have to take an average. I think if it is more than 50, type 1, 15 to 50, they classify as a medium soil and soft soil. So our code, what it says is, the amplification happens only at the long period basically. So now the amplification at the short period are this portion say. So this is not they say that it will not amplify in this portion also. Now this graph was prepared using due to in the olden days, like based on engineering judgment, and then based on the strong motion data set. So this graph has been arrived actually. So now the basin effects, whatever I showed you. So whether these spectra will change or basin will have any effect, So this is a question, we don't know. So we're trying to find out answers for this question itself. So now if you see our Indo-Ganga Basin say, okay, most of you may be seeing this map in Google Earth and everywhere, all of you are this one. So now and then you would have also studied about this map in your engineering geology, how this basin has formed. Of course, I am not a geologist. You would have studied all these things. So now this Indo-Ganga Basin is a huge thing, and this has been formed by the Himalayan rivers. They have deposited the sediments in this huge area. So we have this Indus River, which deposits sediments here, then the Ganga Basin, and then we have this Brahmaputra Basin also. So it is like a huge, some 3,000 kilometers long, or maybe more than that. And the width also is, some places it is 500, some places the width also is very huge. So this is a huge, a geological thing in our India. And now the most important thing here is Indo-Gangetic Basin. It is also very seismically, it is a very active, the region itself. Seismically, it's a very active region because there are a lot of faults, like you can see, which are perpendicular to Himalaya. They run beneath the basin itself, like Mahendranagar Dehradun fault, Great Boundary Fault, Moradabad fault, Lucknow fault, West Patna fault. So many faults are there beneath the basin, and they're perpendicular to Himalayas. And these faults have also produced a lot of the damaging earthquakes in the past itself. Now another major problem in under Ganga Basin is the proximity to Himalayas. All of you know, right? Himalaya is a plate boundary, so there are main central thrust, main boundary thrust, which are very very active faults, and they have produced a lot of earthquakes also. I'm just showing you some historical earthquakes. A lot of earthquakes have occurred in Himalaya. Now the main problem what one sees is whenever there is an earthquake in the Himalayas, say, so although the earthquake epicenter may be far away from the basin, but because of the sediments and the basin, things gets amplified. And people have reported that the damage intensities are 3 to 4 times more in the Ganga Basin, although it's a far away compared to a rock type of site itself. So this is a very challenging how the problem in estimating this amplification in this Ganga Basin. Now this is how I'm just showing you a sketch only. This is not up to scale. Okay, this sketch. So you can see typical how the basin looks like. So these are our Indian Shield, and these are Himalayas. So you will see this Ganga Basin. So now you can see. So these are all the sediments located here. But if you see the shape of the basin, say something a different shape we have basically. So now the question what we are asking is, Anyway, soil amplification is very well known. The one-dimensional soil amplification. Yesterday, the Russian professors also showed you that equivalent linear, that shake, and other things also. So now the question what we are asking is, apart from the soil amplification, so that is a one-dimensional, whether the basin profile, okay, that is the shape of the basin, whether it influences the ground motion in the IG region or not. So this is a question we are trying to ask and trying to find answers for this question itself. So another problem also what we see in Ganga Basin is it's not only the basin. Now if you see, this is a section I have shown here. Suppose this is a Ganga Basin side. This side you are having a huge, the Himalayas. And now everybody knows that if there is a huge topography here, that also, amplifies the ground motion, that also they say. Now this is in the central India. Of course, the topography is very small, but Himalayas, so you can have a huge topography. So this is our IG basin here. So now the question is now whether the Himalayan topography say, so if there is an earthquake occurring in Himalaya or beneath the Ganga basin, whether this Himalayan topography say, it influences ground motion in IG basin only. So we are focusing on IG basin only, but whether this Himalayan topography, whether it plays a role on amplifying our ground motion, of course it amplifies in Himalayas or de-amplifies, but in the IG basin, so what is the effect of this topography on the seismic response of this basin also? So these are very, very fundamental, very important questions which has been unanswered, or we don't know a strong answers for this type of questions. So what we have tried is, of course, today I will be showing you also. I try to find out some answers for these questions by using some type of models itself. So now these are the two questions which we are trying to find out answers here. Now, if you see the literature, say like past literature or the past data, like what people have done in the past, whether they have addressed this issue or whether they have done some the basin and other things also. So and whatever data is available, say. So now, if you see our seismotectonic atlas, produced by GSI, and I think Agok's one paper they have referred also. So they have done, I think, some geological studies or magnetic some studies, anomalies and others. So they have got this basement contours actually. How much is the depth of the basin, and then ONGC, I think some bore logs are available. So they have this type of information is available in the open literature. So they say like the basin depth. So you can see here Sharada depression. So here it is. The basin is almost is a 6 kilometer. The depth. And it is not uniform throughout the basin. So like if you see in Delhi or this place, you can have 1.5 kilometer or 3 kilometer depth only. But if you come to Lucknow and these places, the basin depth increases like 6 kilometers, 7 kilometers, 4 kilometers, and the width of the basin is also slightly more in this area also. So this information is already available in the atlas and from the magnetic studies or tectonic studies. So this depth is approximately available. Now, recently in the last, I think 10 years, the one major thing happened, like this NGRI say. So National Geophysical Research Institute in Hyderabad, they have installed this CAGN network. That is what they call a Central Indo-Gangetic network. So in the Ganga Basin, to understand the importance of all these things, they have instrumented this whole region. Like you can see, so several instruments have been put up. And then they have also instrumented at this rock sites also, where there is a hard rock, like in the Shield region as well as in the Himalaya, to find out the amplification. And then many of the stations are located, in the basin, like where because the basin I showed you, right, different depths are there. So they have instrumented, this entire region itself. And now, fortunately, what happened, we had this Nepal earthquake, 7.9 magnitude, then several aftershocks and several earthquakes which occurred in the Himalaya. So the whole data has been recorded at a majority of these instruments also. So now with this data set, if you look at this data, that is a recorded data, and then if you try to plot them and if you try to find out whether any amplification happens due to the basin, there are some simple methods are there. See, generally, if you want to find out amplification, say, like, this is a sediment site here there are sediments are there. So what one empirical thing what one does is, you correct all these sites for the distance. Okay, you multiply by r or square root depending on the wave this one, and then you take a nearby rock site. Like for example, here ALB has taken as a rock site. So you compute the ratio actual, the amplitudes, and then that itself will tell you how much things have amplified. So now if you see this thing, so what happens is, most of the sites, wherever the depth is high, You can have amplifications, you see 4.5, 2.4, the surface wave amplification, all the waves, a shear wave, how much it amplifies. So this data also shows that there is a lot of amplification, the data also you can get from this data also. And then the response spectra you can plot, and NGRI group has already published those type of papers also from the data, and they have showed that the amplification will be so huge. PGV can be amplified is 10 to 15 times, PGA 3 to 6 times. So these informations are available also. And now what these NGRI people have done is using this data set, receiver function analysis, they have done, this type of thing, and have estimated the sediment depths actually at all these, majority of the stations. And then this, and then we are also having the contours, like, these contours have been come up from the seismotectonic atlas. So these contours, and then from the data set, they have done receiver function, calculated the sediment depth, and then they have updated this sediment, the depth basically. So this information is available. So the sediment depth has been updated, and the same I'm showing as a contour. And then if you show as a, a 3D graph say, so this is a shield region. So you can see the Ganga basin, you see this, you can see how deep it is, and you can see to just get a feel also. So this work was done by, the NGRI group, and this also they have published in, the journals, okay, BSSA, Journal of Seismology, and other journals also. So now by combining all this information given by NGRI, then the seismotectonic atlas and all other things. So this we have prepared a contour map actually of the Indo-Gangetic Basin by interpolating this data, that data, and this one. So this is how the sediment depth map. So the color of the contour shows, you see, the sediment depth here. So in this region, say the sediment depth could be, you see, that Sharada, that region, some 6 to 7 kilometer deep. But as it comes to shield region, say, definitely the sediment depth, it decreases, and almost when it comes to shield, it is 0. But as you go towards the Himalayas, the sediment depth increases. So this information, you see, we have got from all this data. So this information is available. Now, another thing was, if you want to develop any models, say, you require metal properties also. So the NGRI group, so they have also done this. The shear wave velocities also using the same receiver function and analysis, and they have got this shear wave velocity profiles also, one dimensional, but at each station. So this is a profile basically. You can see the red line, and then they demarcate, say. So this is our the IG basin also. So the metal properties also are available. Of course, they are not available in complete 3D or something, but at least with the depth and with the stations, how things are varying. So these informations are available. So now the question is, so now we have some, some idea about the basin depths, and then the shear wave velocities also, these informations are available. So now the question arises, can we do something actually with this data? And then we also have the strong motion data if you want to do something to validate and other things also. So the question arises, you say, can we develop some type of a computational model to address all these issues itself? So we tried to do this one, and of course my research group say at IIT Madras, because I'm in a struggling department. So our research group basically, we have been working on this numerical methods. So analytical methods also we work. We also do numerical methods like, you say, finite difference method, finite elements, spectral finite elements, finite volume methods, and pseudo spectral methods, and of course analytical things also we have been doing here. So previously, we have done build a huge computational models basically. So like you see, we have developed a huge computational models for simulations of the earthquakes in our computer itself. So I'm just showing you some samples which we did 10 years back. Like this is almost 12.7 billion degrees of freedom at a 2-kilometer resolution, say. So this is a finite element model. So this for the globe, we have been doing this one, and we have used this to simulate Sikkim earthquake, Gujarat earthquake. So those papers are also available online, and you can also see this one also. So, and then this is one of the recent things which we did, like for the peninsular India. So we have developed a huge computational mesh actually, okay, so which can simulate the ground motions. So these computational models, say, so they are very, they are huge models only, but they work very nicely, and we can simulate ground motions. Like for Gujarat, so you can see the data and then simulate it, say that the black one is recorded, red one is simulated. We got these models are working, and they agree nicely, with the data itself. So the question what arises was whether we can use these models to build same thing we can do for the Ganga Basin or not. Now these are the so we use right now the spectral element method. So this is one of the powerful method, and the codes are also available in the Fortran codes in the open domain. So any of you can download also. So this method. So now, of course, the method is also same as finite elements, what we do in civil engineering itself, but the methods of integrations are slightly different here. So these are basic, the equation of motion in our continuum mechanics. You would have studied in your BTech, that simple bending theory and other things. So instead of that is, you write in terms of bending moments and shear force, but if you write the equation in terms of directly in terms of stresses or displacement, this is the overall, the equation. So I'm showing you displacement equations of equilibrium. And we have the boundary conditions also. So generally, like surface is stress-free, absorbing boundary conditions you have to use at the edges. So the boundary conditions are also very well known actually. Okay, so using these boundary conditions, you can solve any problem. You can model a beam, you can model anything. So now we use these equations to model our the Ganga Basin itself. Now, what the spectral element method does say. So this is basically the strong form we say. So this is a strong form, the equation of motion strong form. So strong form means you want this equation to get satisfied, so each and every point inside your medium. Now there is what we call as a weak form. Okay, so where we say that the equation should not, we don't want that equation to be satisfied at each and every point, but it has to be satisfied in an average kind of a sense or an integral basically. So this we call as a weak form. So this weak form is fundamental for finite elements and all those the methods itself. So this equation is the same equation only. So we are not using strong form. We use a weak form, that is the integral sense we use. So this is our equation. So if you use separation of variables, say time and the space, if you separation of variables if you do, and substitute in this equation, so we get this equation itself. So the equation is in terms of u of t is separate, times are separate, spaces are separate itself. Now here what to do is, so this portion so this you can write it in terms of a mass matrix and stiffness matrix. So you can write your equation like this. Your mass matrix is this expression, and stiffness matrix. So these terms only. This itself is my stiffness matrix also. And then the force term this expression, that is a phi I, if you write in terms of f of t, so you will get an equation as a a multi-degree of freedom system, which you would have studied in structural dynamics also. So now this is basically a second order ODE. So you can solve, there are many methods you would have studied in dynamics, so finite difference, that Newmark method, so many time schemes are there. So if you use the central difference schemes, you can write this as, if we denote the t of plus delta t, and then if you use u of t and old is ut minus dt so you can use this equation to as a time marching scheme we say, to find out t plus delta t. You can iterate and you can get your time history. Now the most important thing in this approach is this the calculation of inverse of a matrix basically. So this is other things are all straightforward only, but if you want to do it on a computer inverse of a matrix is very challenging actually. Okay, and if it is not a a diagonal matrix, if it is not a symmetric or asymmetric, it is very time consuming. And when you want to develop these type of huge meshes actually of billion degrees of freedom, so if you want to invert a 1 million by 1 million matrix, so it is a huge time consuming on computers also. So what this spectral element method, what this they have done is, now in our ordinary finite elements what we do is the integrations we use a Gauss quadrature rule basically. Okay, and then the Gauss quadrature, and then the points where you are interpolating the polynomials, they are entirely different in ordinary finite element. So in spectral finite element, what they do is the points where you are integrating, and then your integration points, and then where the points which you are using to represent the polynomials, both are same actually. And then they use this Gauss legendary Lobato, this new integration scheme actually. So this is a it is also more or less like the the Gauss quadrature one, but slightly different. So these points are used to represent the function as well as the integrations also. We use even the endpoints also, okay, to do this, to calculate these integrals. So the advantage, so now, so if you want to do in 3 dimensions, so we use these hexahedral elements. So which is, the 27 degrees of freedom, or 27 nodes are there, you can count those, it's higher order polynomials we use. So we use the shape functions, and any function can be represented by this Lagrangian, the polynomials. So same like whatever we do in ordinary finite elements. So Lagrangian polynomials are used for a shape function as well as to represent the function itself. So you can find out the derivatives, and you can also do this integral, say in 3D, using this Lagrange polynomials, and you can simplify by this, the expression itself. Now, because of this GLL quadrature, say, because of this most important thing like your integration points as well as the interpolar, because both of them are same. So what happens is, this is a thing which happens in this one. Yeah. So what happens essentially is this integral, say, that is rho w dou square t, this d cube x, this integral, that is which controls this mass matrix basically. Okay. So rho is the density of your medium. So this mass matrix, what happens is, so because of this, the GLL quadrature and all other things. So when you try to integrate them, so when you do this displacement and this one, so the integral finally it boils down to like this, and the mass matrix becomes, you see, a pure diagonal matrix. So all the off diagonal terms are zero. Only we have the diagonal term. So this is the greatest advantage in SPECFEM. So when the mass matrix is a diagonal set, so now the inverse of is very easy to calculate, and then your computational efficiency or the computer things becomes very not so much of time consuming. So automatically, and it is very easy to implement on the high performance computing, the parallel coding and all other things can be done very easily with this spectral element. Ordinary finite element, what happens is the mass matrix will not be diagonal. So then to invert the diagonal non-diagonal matrix, say that you have to have the computational efficiency or the memory and other things, they increase in the finite element. But in spectral element, this is the greatest the advantage. So diagonal matrix, it's very easy to invert, and you can easily solve this very efficient on a per computer. So now the SPECFEM 3D set, it is already available open source code. You can type in Google, you will get this one. So this is basically, it is not a software where you can do just click kind of thing. These are also some Fortran subroutines they have given basically. Okay, so now you have to download these Fortran subroutines, and they work on parallel computing. Okay, so they don't work on ordinary computers. You have to rewrite the code. So parallel computing you have to do, and then you have to compile. And there are issues like that. So like you see, if you are doing machine to machine, so like IBM or some other compilers if you are using, so you may have to run some some more subroutines or something, and you have to implement this on the supercomputers. So what we have done is we have already implemented this code. It took a lot of time in our supercomputers, and then we have written some subroutines also to process the data, and then to define the finite faults and other things. So there's some subroutines we also developed, but the main code comes from this SPECFEM 3D Cartesian actually. So now we use this spectral element method, for our to simulate ground motion in our Indo-Gangetic Basin also. So now, as already I mentioned, the first step is the basin depth, and then the velocity models. As already I showed you, we don't have 3D things at all, but only with the depth things are varying. Some one-dimensional models are there, and roughly we know the depth also. And recently, many IASC group and many people, or even the Ministry of Earth Science, they have done microzonation studies like Lucknow and other places. So that is only the top 30 meter or 50 meter or maybe 100 meter, they would have gone. Even the Ayodhya temple also, that MSW NGRA has done. So we know that only the top informations are available. So whatever information was available in the top layer as well as sediment depth, so we incorporated everything in our the finite element model itself. So we have done, I will be showing you results. So the whole Ganga basin, it starts from Indus River and the end Brahmaputra basin, everything has to be done because of computational difficulties. We have divided that into two pieces actually. So one is in the Delhi region, that is this Delhi region we have done one mesh for this Delhi region. Other one is for the Nepal region because the data was there in. So this is our finite element meshes basically. So the material properties, so we have, because the basin depth is also different, because the Sharada Garj I showed you, right? So there are basin depth also varies. So this is for the Nepal region basically. Okay, this is the depth-wise shear wave velocity profile, and this is for our that central seismic gap, the near the Delhi this region say. So all the metal properties, everything has been taken from NGRI, and we have interpolated and given this metal property to each and every element in our finite element, that the spectral element, the photon codes. So now after developing these all the layer wise metal properties and all other details, so this is how the basin looks like. You can see. So the things are, of course, it is up to scale. This map 20 kilometer, but basin depth is 6 kilometer. You cannot see in detail. You have to zoom. So this basin profiles has been captured in this model itself. And then what should be the size of the element, and then the time step, the stability issues are there. So you have to do all those calculations. You can't take because it's a dynamic simulation, say. So the element size, the delta T, stability, all those things have to be checked. The current stability condition, others also. Like this is like you see, this is a mesh for the Delhi. So Delhi is located here. So you can see the Kedarnath and others, Mount Kailash. So this also the topography has been taken from that SRTM website. So this also has been incorporated here. And now this is another mesh which I'm showing you for the Nepal region. So you can see Kathmandu also there is a basin in Kathmandu. So that also their metal properties have been changed, and you can see this is a Mount Everest basically. Okay, so because this mesh is up to scale, so you cannot see you can see this topography also. So depth is up to 60 kilometers. The depth we have modeled, and if you zoom, you can see the sediment layers, how the Ganga basin say this looks like. And then you have to do some mesh doubling and all other details. So all the things have been done, like stability, all those things have been checked actually. So these are some, whenever you are doing finite elements, so you have to report all these numbers, like you see how many, what is the domain size. So this 660 kilometer by 440. So this is 660 and this is 440 kilometers. So the length and width of, and of course depth is 60 kilometers actually. So this much region has been modeled. And now you see the depth is 60. Now we are using this hexahedral element. So it's a higher order 27 node element here. And these are the number of spectral elements actually on the surface. And along the depth is 37 because you have to do because the mesh size also depends on your shear wave velocities also. So this is a minimum size of the element. So because our computational difficulties, we were able to go up to 0.8 kilometers element size and 0.57 on the surface, and with depth site is 0.4 kilometer. And maximum size, this element will be at the bottom almost actual. Okay, so where you don't require that much accuracy. So 3.4 by 2.28 by 2 kilometers. And the GLL points are this many million, and totally the degree of freedom is 1.16 billion degrees of freedom. And delta T also you have to estimate from your stability criteria. So we have what we call as the current stability. Okay, so we have this stability criterion. So using this so we calculate all the details. So now this type of, as already I mentioned, so this doesn't work on ordinary desktops or laptops because the element size is so huge. So what you have to implement this in our supercomputer. Now at our IIT Madras, we have what new supercomputer from IBM, this one. So which is, we call this as a aqua cluster actual. Okay, so this has been commissioned last year. People have started using. Before that also we had a old computer, but this the updated one which we got last year. And this has something like it's a 280 CPU nodes and then 40 cores, and the RAM is 192 GB RAM each node has. And then there are also GPU nodes also are available, and then these are storage configuration like 1 petabytes, so all the details are there. So this supercomputer is available here. So what we did was we implemented all the Fortran codes and our metal properties, everything, and then we started simulating in this server. So now these are the results actually. So to first, we have the data for Nepal earthquake. Okay. So this has been provided by NGRA. So Dr. Srinagesh so who is also now, professor of practice at our IIT. So he has applied us all the data sets to find out, how, whether our model works or not, this simple computational model So I am showing you the comparisons at, Varanasi, Amedi, Faizabad, all these stations itself. You can see the black is the recorded one and the blue is the simulated one basically. You can see, and this is, we are also showing the basin depth, the contour basically. So you can see the comparisons are, it matches very nicely the phases, the amplitudes, and the type of surface waves. All those things, is captured by this computational model. So this is in radial direction, and this is in the transverse direction. Because why radial and this tangential? Because we wanted to find out this Rayleigh wave, the love waves amplification, whether it is able to capture properly or not. So this is the transverse or tangential component. You can see the comparisons are very, and we have done some misfit calculations also. So they are all within the limits, which shows that this model is working nicely in reproducing this data also. Now these for the vertical component, you can see this is Varanasi station, and then this BRP station, say it is located at the very deep basin is there. Amplitudes were less here basically. So you can see the model is also able to capture. Now Varanasi, these are far away. You can see the amplitudes also they match very nicely with the data. Now this is for the main shock. So the main shock magnitude was, I think, somewhere around 7.86 or something like that. So now because the magnitude is so high, say the point source models, that doesn't work basically. Okay, so you have to use this finite source models itself. So I think many after this earthquake has occurred, say. So I think many groups like Japanese group, then American group, they have worked on this data, and they've estimated this finite fault slip models. They say it is something like a crack, the slip, whatever, these models are is available. So now these models have been derived based on the Kathmandu, there was a strong motion data was there. So they used this at the Kathmandu station, then the broadband records, the teleseismic records, and then they developed this finite fault source models. They have not used our IG data to find out the slip on this one. So what we tested was we used this finite fault slip model, and then we tried to compare with the data basically. So you can see, so here also, most of the features are nicely captured by our computational model, but there are some differences are there. So these differences basically, we can attribute, because this data has not been used to find out this slip models maybe, okay? One can attribute to this one. So that is a radial component. Then this is a tangential component. You can see Varanasi, we will get excellent comparisons, but at BRP, say, this is basically because this slip has been obtained from the teleseismic and then the Kathmandu data only. So like this, you see, we have got all the comparisons, and the comparisons, if you do the statistical calculations and misfit functions, errors and other things, so they are all within the limit only. So which says that our model is statistically significant in reproducing, you see, this time itself. And these are the peak ground velocities. Okay, so these are the velocity, the contours. Okay, so for the Nepal main shock, so for the Nepal main shock, because now once you have a computational model, say, so once the computational model has been calibrated, so you can obviously simulate wherever place you like. Okay, so for the Nepal main shock, so we simulated this time histories, and then the peak ground peak values have been obtained. So you can see this main shock is somewhere located here. So this region, say, because Himalaya topography is also there, the values are not like axisymmetry kind of thing. And if you see in the basin, although they are very far away from the the main shock, but still you have this very maximum values located here. So the reason is because of the basin as well as the sediments. So things got amplified. So now this is for the radial component, and this is for the transverse component, and then this is for the vertical component also. So you can see the contours are also no axisymmetry because of the finiteness of the source, and of course the topography as well as the basin, and then this sediment effects. And of course the PGV, you can see some maximum 20 centimeter per second we have, and here I think something around 14 centimeter per second we get these type of numbers also. And now to understand the basin effects, we have also put stations like this P1, P2, P3, these type of stations, like equally spaced, but they're varying, the basin depth. Of course, P1 is located in the Himalaya itself. So P2, P3, P4, P5 is perpendicular, to understand what happens, we just try to simulate at these places also. So these are the places. Like now here, what we have done is to understand the amplifications. We have put stations at rock also, where the sediments are there, and then at the surface also, and then you can easily find out how much things have amplified. So now this is at a P1 station, so that is which is located in the Himalaya. It is not located in the basin. So obviously the both of them will be same, but the P2 stations where the sediment depth is around 5 kilometers, okay, that is located here, which is very large sediment depth. You can see the red one shows at the bedrock level, this black one shows at the surface actually. So your 0.7 is at rock, but at the surface we get is a 4.9, almost 5 to 6 times things have amplified. Now, similarly, so these for the transverse component, you can see 0.6 to 3.6. And of course, there is also de-amplification is also. So 3.8 to 1.8. So this is somewhere de-amplification also you can see. Then P3 station, say sediment depth is 4 kilometers. You will see amplifications, and of course a P7 station. If you see more or less, it is located in the shield region. Sediment depth is very small, like 500 meters, say. So more or less we get same thing, but some small amplification also, decreases. So this is one important things which we have observed. Now, apart from this, we also simulated at important locations also, like so these are the places where damages have been observed, like Gorakhpur, Dioria, like Dhaka. It's not in Bangladesh. It is some small town in Ganga Basin, Motihari, Muzaffarpur. So here also we have computed at the rock as well as at the surface. So to find out to see how much things are amplifying, and we can see wherever the sediment depth is very high, say the amplifications are extremely high. But wherever the sediment depth is small, or then obviously the amplification also will become small. So these are some numbers actually. So like for example, if you take the station, say like Gorakhpur, the sediment depth is 6.1 kilometers. So you can see 0.3 is at rock, at surface it is almost 5 actually. Okay, huge amplification. Now this is in radial component, then the tangential, then we have the vertical component also. Huge amplifications you can see. Now if you see a place where less sediment like Patna, 0.9 kilometers, say. So then 900 meters sediment depth, you can see 0.7 to 1.6 only is the amplification, 1 to 2. So as sediment depth is more, obviously the numbers are extremely high, like 5.6 you can see, or 5.7 say. 0.8 to 8 times is the amplification at this place. And of course, these amplifications are for velocities, okay, not for PG and others. And as already I mentioned you, the data also say, like NGRA people have estimated velocity will have amplification from almost 5 to 15, they have reported, and our simulations also, will get the same things also for velocity. Now to understand this basin, say, what we have done is we have done some simulations actually, because once the computational model is ready, we can do all the things. So to understand soil amplification, basin amplification, say, so we created several models also. Like you see, this is a one-dimensional model. So no basin is there here. You don't have any basin. There is no Himalaya also. It is just a uniform actually, just one-dimensional. So metal properties are varying only with respect to depth. It's a uniform model kind of thing. Then we have also created a model like rectangular basin. So assuming that Ganga basin is just a rectangle, and then you are having a Himalaya, metal properties are suddenly changing actually. Then another model was the 3D model of the Ganga basin. So this model also has been incorporated. Then another model was the topography of the Himalaya. You can see, because these are up to scale, these values appear very small here. So variety. So in these all these models, the topography of Himalaya is not there. But we are putting a topography in the last model. This is exact actual, okay, because the 3D is there, topography is there. So we try to find out, what each and every aspects, how much it will affect, kind of thing also. So these are the simulations, like case 1, case 2, case 3, case 4. Now, if you see this case 1 side, it is just one-dimensional kind of thing. Now, once suddenly the Himalaya comes into picture, you can see the nearby stations say. So now we have put stations like this, okay. So one perpendicular kind of thing. So 1, 2, 3 are in Himalayas. Okay. So they are on that mountain. Then 4, 5, 6, they are in the Ganga basin. So if you see, say, once the metal properties change, because Himalaya, the sediment depth comes down, the values reduce. This is for the radial component I'm showing you here. So now if you see in the basin, say, now the one-dimensional model, these are time histories are like this. But once the Himalaya and the basin comes, you can see these type of extra, the waves which comes into picture. And if it is a basin, you can see, the 3D model say. So you will see this type of, extra, the surface waves or whatever, they also get generated. And if you see this station, the amplitudes of surface waves will be more than shear wave. So all these patterns, you see, we have identified, to a better understanding we got from these simulations also. Now, when there is a topography, say, topography, Himalayan topography at RC for this station, or maybe here, there are effects are there, but as you go far away, the time histories are more or less same as the topography, because 500 kilometer far away from here, 400. So the effect decreases, but some small, the wiggles come up, but not so significant because of the topography of the Himalayas on Ganga Basin stations also. So this is for the radial component. Similarly, the tangential component. So you can see some components you will see effect here, like you see the one-dimensional model. So TC4, it is like this, but suddenly it amplifies with basin and then topography. And then so you can see 1D it will be like this, but when topography is there, say automatically it comes down. But at far away places you will see these type of the love waves or surface waves. You can observe at this side. And here is a vertical component. So vertical component also, you will see the similar type of features also. So this tells you, the basin also plays a major role. And if you don't model the basin, say, then you may be, the surface wave amplification, other things we may be underestimating. So now these are the amplifications, for peak ground velocity. So the automatically 20 times, we get the amplification. And of course, maximum amplification you will get at a place where the basin depth is extremely high itself. So Gorakhpur, this is region, say, the maximum amplifications are observed also. And this is well in agreement with the data also. More or less the same numbers one is able to get. So this is a vertical component, all the three I'm showing here. So now if I plot them, say, the amplification as a function of basin depth for the Nepal, whatever simulations we have carried out. So at all the stations, just to plot them, you will see a nice, beautiful pattern actually. Okay, like how the amplification you see is increasing with the basin depth. So we have 7 kilometers, so amplification is also very high. So the average, you can say up to radial component 15, then the maximum is 10, the average numbers. And vertical, say, you will see up to 6 kilometers or sorry 6 times amplification is going to happen from the bedrock to the surface top of the basin itself. And then here what we did was we did some because right now in hazard analysis everybody uses ground motion relations. So all the NGA, the West equations we have taken, and we have given VS30 also as 180 meter per second, and these are the attenuation curves basically. Okay, for some 7 magnitude earthquake we are just plotting here, and then we plotted our simulations data also. So what happens is our simulation data, say, so what happens is it very well agrees with the GMPs, but wherever the sediment depth is high, say, so the GMPs are are not working, or they are underestimating our the P. Of course, we plotted only peak ground velocity, so this underestimating happens. So the basin effect, it dominates, and then so this plays a major role in the GMP, in the development of GMPs, and then to understand the hazard for this region itself. Now I showed you in the Nepal region. So similar thing we have done for the central seismic gap in the Delhi region, because Delhi is a capital city, say. So everybody is interested, how Delhi responds if there is earthquake, and a lot of financial things are there. So how this, and many people say that there is a central seismic gap in the Himalayas, so this produces 8 magnitude or 8.5. So what happens to Delhi, or how this Ganga basin behaves also. So same computation procedure is same, only the region is different actually. And of course, this also has been validated, and all the statistics, everything has been done for local, some Delhi events, and for the Himalayan events also. So these are the mesh details actually. So this was the mesh, the region 760 kilometers by say 910. 180 kilometers of depth, and these are the elements we took it, and the degree of freedom is 20.3, and this was our time step basically. So using this, once again, we simulated our the computational models. Now this mesh was, because the mesh was very high and there was issues, so this mesh was run in KAUST actually, that is King Abdullah University of Science and Technology. So there it was run, and Professor Martin also, so he helped us in carrying out this simulations. So we see, and now here what we tried to do was, anyway in Himalaya if there is earthquakes, Nepal, we already know. But if earthquake occurs beneath the basin, that is this Mahendranagar Dehradun fault, if it occurs beneath the basin, how the response will be? Because the basin is like this, it is not like a, this type of a shape. So if the earthquake occurs here, what happens? If earthquake occurs beneath the basin, the entirely it responds in a different fashion. So this is our finite fault slip model, Mahendranagar Dehradun fault we have taken, and then we put receivers in all the directions, and we try to find out any pattern emerges from these simulations also. So here also we see because it is a strike slip mechanism, say. So we see like radiations and all those things, we get from our analysis also. And here also things gets amplified, like 16 times from the rock to the surface here itself. The amplifications are huge. So this is, I think, the horizontal component, rho to the 50, and this is a vertical component. Okay, so the vertical component you can see at far away places, say we have this amplification also, because this is something like we have a basin and we also have this rock outcrops also near Delhi and this one. So if you model them, so you will see the waves are getting trapped, sediment or something like that. So you will see these type of small amplifications in local pockets actually. Now this same thing, I think all the three components I'm showing you here, vertical, all the three are there here. So the same pattern you can see, and this radiation also, say you can see, the rupture, how it is going, this also, one can observe in these simulations also. So now these are some numbers, okay. So like Delhi, if you see, say how much things gets amplified, like PGV, say, what is amplification? Then spectral acceleration, T is equal to 4 seconds, 8 seconds, because these are long period things itself. If there is earthquake occurring below the Mahendranagar fault, how much these numbers vary. So these numbers also has been obtained actually for this Delhi city. Now, another thing recently what we have done is the spectrum, this finite element models, because we don't have detailed metal properties and others, so they can simulate only the low frequencies, very nicely. But what about PGA? Because you would have observed, I have been talking about velocity. What about the accelerations? How the things change also? And because we don't have a good quality, wide 3D variations or something like that. So what we did is this hybrid models are there. So now these models are very popular and whole, all over the world, they're using these models for simulating this ground motions also. So what we do is the low frequencies, say, we simulate from our spectral element model, and the high frequency, that is 0 to 0.4 hertz. In some cases we go up to 1 hertz or 2 hertz also, because based on the element size. And then we use this scattering parameters also. So we have this isotropic, that scattering theory by this Jung. Okay, so this also we use here to simulate the high frequencies, some 1 to 10 hertz we do, and then we combine both of them, and then we simulate this broadband, that is the time history which is valid from 0 to 10 hertz. So this is what you see, we try to do this this methodology we try to use for our Ganga basin also. And of course, we have to calibrate all the inputs. So whatever data we have set, so we calibrated all those issues, and finally we simulated several scenarios, and we have got all the response spectra, time histories, and others also. So this is how the broadband method. So this portion is simulated from higher scattering theory. Low frequency is simulated by low frequency. So we match in spectral domain, and then we get this numbers also. So we have done the calibration is very important, because scattering parameters you have to do. So that we have done statistical analysis and calibration. So like damping, the kappa factor, and all those things, we have calibrated with the strong motion data itself by comparing, several statistical tests are there. So we have done all the calculations, and this is one simulation I'm doing, like the calibrated one, say. So this station is located in the Himalayan, depth of basin is 0. So you can see how the response spectra is recorded and simulated, say how that they match very nicely, with the data itself. And if you do that misfit calculation, say, so it shows statistically it is significant only. Now this is at a place where basin is there, 3.36 kilometers. So here also you can see, of course, some because the simulations are valid from 0 to 10 hertz. So some small things are there, but overall in agreements, they are agreement with the simulated, the recorded data also. So like this, we have calibrated our broadband models also for the entire this Ganga basin. So we use these simulations to find out for this hypothetical earthquake. So most of you may be knowing, in central seismic gap, they say, right, some 8.5 magnitude is going to occur. You would have seen many papers also, and many people have simulated also for this earthquake. So what we did was we used this to, because our computational model is ready, say. So we used it, we tried to simulate, how the ground motion will be in the Ganga basin for this hypothetical event. So this is the same mesh I showed you. We have put stations to understand basin depth and the radiation and other things also. So we use this slip model because it's a hypothetical event, right? So we don't know what type of slip it will have. So we have our non-Gaussian random slip model. So recently we have published also that one. So we used that slip models, to generate randomly some 30 samples or 40 samples, and for each sample, say, we simulate from our methodology. So these are some time histories, like you see Haridwar, then Chamoli, Tehri, the acceleration time histories. Because now these things are broadband, Roorkee, then Kashipur. So we have got all these time histories, and then the response spectra also. So I'm just showing, some comparisons. Of course, because it's a very hypothetical earthquake, magnitude is very high. So obviously it will be more than the codal provisions, because the codal provisions are for average kind of thing. So because it's extreme events, so Haridwar very near the epicenter, it will be much higher than the IS code itself. Of course, as you move far away, say, things may be fine, like at Delhi and other places, say. Of course, some places you will have amplification, but some it is on the overall the agreement. Like Kashipur, IS code underestimates, obvious, because it's 8.5 and this is a design spectra. So with this, I will just summarize. I think time is 11 to 12 only. Okay, so I will summarize whatever I spoke. So I spoke about the seismic amplification in the IG basin. That's what I have spoken today. And of course, as already I told you, not only the site effects, say, the shape of the basin basically. Okay, so whether it is a parabolic or foreland, or whether the variety shapes are there, so that plays a major role. So our IG basin is something like this type of a shape. So it has a lot of effect on the amplification. So if earthquake occurs in Himalayas, you will get a different amplification. Suppose if earthquake occurs below the basin, say, the amplification is entirely different itself. And if you don't consider the basin, say, then the surface waves and others, you may be underestimating the amplification also. So this we have showed the importance of this basin effect. I have shown you in this, the important thing itself, and then I have shown you results, for the Nepal region, as well as the seismic gap that is in the Delhi region also. So both these things I just showed you some computational models, and then the results also. Then I have also shown you the amplification of PGA and the PGV. So PGV, 15 times, 20 times, where basin depth is very high, the amplifications are also very high in all the
in progress.
And then I have also shown you this, the high performance computing. So these type of simulations, say, so you can run only on supercomputers, because the degree of freedom is very high. So you can run only on this type of supercomputers only. Now the further challenges, say, the future scope or the further things, if you see, now I have commented only on the basin effects and the site effects. But now how do we integrate, say, these results, how to use this, whatever we have simulated, with the seismic hazard analysis and design of structure? So this question we have not answered. So right now in the IS code, as already I mentioned you, type 1, type 2, type 3, we have the long period amplification is there. But how do I incorporate these basin effects in the design codes? Say, that is still a challenge actually, okay, because the basin depths are different. So how do we handle these things is still a challenge, and it is still an open problem. So this, if some of you followed it, how do we design structures, say, in the IG basin? And all of right, recently in Ganga basin is full of the financial activity, like Ayodhya temple. Yesterday our prime minister has inaugurated the Kashi temple, Kashi Vishwanath temple. So many very important structures are getting built in the basin. So how do we take these results, and how do we design those type of structures where you have sediment depth is 6 kilometer, 5 kilometer? So the design itself is a big challenge in this area. Okay, so this very challenging thing. And some of you, if you are doing for your PhD or master's thesis, you can take up these type of works as a civil engineers. You can try to understand these things also. Then another most important thing is this urban earthquake engineering, because these computational models, they can simulate anything. Now we can also find out seismic response of cities also. Like Delhi nowadays, people are doing micro zonation, and then the shear wave velocity, how it is varying in the cities. That itself, many reports, many people have published it. Like Lucknow also, we have a complete 3D profiles are available. So now how a city responds. So if there is an earthquake, so which part of the city will be more damaging, which part of city will be less damaging. So and where the things will get amplified much more. So this also one can study, using this type of computational models. But the element size has to be very, very small. Right now, whatever simulations I have shown you, the element size is 0.8 kilometer or something, but when you are trying to do at a city level, say, you have to come to meter level basically. Okay, so this also is a very, very important area which one can explore through this type of computational models also. And we can also, add another layer on the top, the buildings also. That also in finite elements, anything, whether it's a soil or a buildings, it doesn't matter. We can use the same elements, and you can put the, the structures also on the surface here, and we can study using this computational model. So directly the structural response itself, not even the ground motion. So this is another challenging thing which some of you, can explore in your PhD or master's thesis itself. Now, of course, another thing, is machine learning also. So here the problem, as already I told you, this type of large codes, say, you have to run on supercomputers, and they take a lot of time, 2 days, 3 days, something like that. So the idea is, if you can do something like a machine learning, like you say from the simulations, if you can design networks, say, if we can design artificial neural network to understand all the patterns, and then and because we are simulating on a whole grid, large data is getting generated. So this is also very interesting thing, and now everybody is talking, right, artificial intelligence and machine learning and this large data analysis. So this also can be explored actually. Okay, so for some of you, if you are interested in this areas, you can do some of these problems, very, very challenging, and very, very, there is a lot of scope for innovation also in this problems. So whatever I spoke today's lecture, is some of these works have already been published. So if you want to know more details, so you can download these papers, soil dynamics, earthquake engineering, then Journal of Earthquake Engineering, Bulletin of Earthquake Engineering. So these papers are available online. So if your institute has not subscribed, so you can get these PDFs from my ResearchGate website. So all of you, if you are doing research, you can create it is a free, ResearchGate, and you can request the papers automatically. We can send it to you also. And nowadays the current trend is, because of online, you see the lectures, everything has become online. So now I have my own YouTube channel also. So if you want to know more about spectral element method, the computational things, or I even mentioned you in the starting the seismic zone map lecture, which I gave last year, so all the lectures are available in YouTube. So you can watch this, and you follow it. If you have any questions, you can ask, I will reply also. So all the lectures are, because things are very open nowadays, are available in YouTube. If you are anybody is interested, say, you can see this, and you can go ahead with this lectures also. And of course, I have to do acknowledgements. Like, of course, I acknowledge the CED39. Okay, this is a panel. Okay, which is responsible for the zone map. Okay, which is a committee. It is not because inputs comes from them, but the work I have carried out. But now, of course, I acknowledge strongly, this Dr. Srinagesh. Okay, he's from NGR. He was the person who instrumented that CIGN network, and he only provided us the data. I think without that, we could have not developed our computational models. And of course, the PESMOS database by IIT Roorkee, they also did a wonderful work, and they kept all the data in the open domain, so anybody can download. So with those data only, we were able to build these type of models also. And of course, I acknowledge the National Disaster Management Authority, for their support. And of course, these are my PhD students, like Dr. Jayalakshmi. She is now doing a postdoc in KAUST. So she did that computational models. Of course, Danya, she is also helped me. And of course, Srija, who is doing currently PhD, with me. And so she did that Nepal work itself. And of course, I also acknowledge Professor Martin Mai. Okay, now he is editor of BSSA journal. So he helped us in that broadband simulations, because they have done long back this broadband simulation, that the high frequency thing. So he helped us, and of course he suggested us, you see, in doing our broadband simulations. And when our server was not working, so he helped us to carry out these simulations in the supercomputer, which was there in KAUST actually. So we used their supercomputers for that central seismic gap set, in their university. Of course, my postdoc, she is doing postdoc with Professor Martin May only. So that is how this happened. So finally, so thank you all of you for your patience, you see, for listening to my lecture. And if there are any questions, I'm open. So thank you so much.